I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So, kind of got a little bit hurried at the end of last class. I just wanted to say, here's an example of something kind of like the question that was asked at the tail end. If you were going to integrate, I don't know, x to the 113th power times e to the, I don't know, x squared dx. Suppose you were wanting to integrate such a thing. I suppose you probably could make a u equals x squared substitution and maybe do integration by parts like, I don't know, 20 times or something. Figure it out, right? Or you can find a power series solution. And here's how that's done. You just take the integrand. You find, by some method, in this case I'll use substitution, right? You find a power series representation for the integrand. All right. Almost there. Clean it up. You do need to simplify the power series for the integrand before you actually make the critical step here. So this is 2n plus 113 divided by n factorial. There you go. At this point, I have an honest-to-goodness power series centered at 0 for the integrand. And so then I can integrate term by term, right? And so I get a constant plus the sum, n equals 0 to infinity of 1 over 2n plus 114 times n factorial x to the 2n plus 114. And there you go. This is a power series solution to the integral. Yeah? And for this kind of problem, it's about the best you can hope for, right? And that's not a bad thing either because, that is it's a power series representation of the antiderivative here, which means I can approximate the antiderivative in terms of polynomials, Taylor polynomials, as high as I want. I can get as close as I need to for an application using this formula. I mean, fine, it's not just an expression in terms of exponential sines, cosines, so-called elementary functions, but it's the next best thing. So, questions? Yeah.
You're from the first step. I don't really understand that.
So, the basic thing here is e to the u is the sum n equals 0 to infinity of u to the n over n factorial, right? This is one of the things you need to memorize. Another thing you need to memorize is this. Another thing you need to memorize is this. And I could go on. There's about, 3 or 4 more things to add to that. But what I was doing there was just using the known Maclaurin expansion for the exponential, plugging in u equals x squared. Does that make sense? And then multiplying by x to the 113th, of course. Other questions? So, question about the homework then. Particular problem you guys are stuck on? 101. Find the power series centered at x equals to 1 for f of x equals to x squared plus cosine of x plus e to the x. I think I would use substitution on this problem, probably. I mean, you can either use Taylor's theorem directly and try to look for the pattern, or you can use substitution. I mean, either way is probably about the same here. What was your question? I mean, were you just stuck on how to start it, or?
Yeah, I actually asked about 101, but
You asked about 101?
yeah, but it's okay.
Oh, I was talking about 100. But you want me to talk about 100 anyway? Okay. Here, let me do something similar. If I had f of x equals to, say, x squared plus the sine of x, right? Plus e to the x. And I wanted to find power series centered at, let's say, x equal to pi to make things a little bit simpler. How would that look? What would that look like? I mean, you got choices, right? You can either calculate the derivatives of this to arbitrary order and look for a pattern. Maybe that's not too bad here, right? If we use my substitution trick, though, it looks like this. So I would do this trick. I would say, okay, so that's really x minus pi plus pi squared plus the sine of x minus pi plus pi plus e to the x minus pi plus pi. So the last two terms, so the first one gives me an x minus pi squared, right? Plus 2 pi x minus pi plus pi squared, just foiling that out. My goal is to keep copies of x minus pi, because to find a power series and centered at x equal to pi is basically to expand in powers of x minus pi, right? You're wanting to expand in x minus pi. That's what that would mean. To find a power series centered at pi means you're trying to rewrite the expression as a sum of series built from x minus pi to various powers. So that's what the quadratic is. The sine, well, I can use adding angles formula for sine. That's sine of x minus pi, cosine of pi, right? And that's it. What's the other term? Sine pi, right? But this is 0. So that drops out here. That won't happen in problem 100, right? In problem 100, you're expanding around 2. So the similar step for problem 100 would produce non-trivial terms for both the sine and the cosine. This, by algebra, is e to the pi, e to the x minus pi, right? So what you're looking at here is pi squared plus 2 pi times x minus pi plus x minus pi quantity squared. What's cosine of pi? It's minus 1, right? Now, again, for the problem 100, it's not so nice. You're going to have like a cosine of 2 and a sine of 2 in your answer, right? But here it's minus 1. That's nice. And then plus, well, let's just say minus the sum, n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial x minus pi to the 2n plus 1. What am I doing here? I am using the known Maclaurin expansion with a substitution of u equals to x minus pi in my formula over here, right? I'm putting u equals to x minus pi to convert to the power series in x minus pi. I'm using the known sine series. And then, of course, this guy, plus e to the pi sum n equals 0 to infinity of x minus pi to the n factorial, well, over to the n divided by n factorial, rather. Now, the best answer here combines terms which can be combined, and it separates out terms which are sort of outliers. That would be the best answer. So clearly something different happens at orders 0, 1, and 2, right? Up to quadratic order, you've got that x squared piece, which is really kind of an aberrant feature from the general pattern here, right? So like, I would say a good thing to do at this point is to separate out the constant terms. And, you know, sometimes now it's a nice thing to fall back on Taylor's expansion. I mean, you don't have to put all your eggs in one basket. You can use a combination, right? What should the constant term be here if we remember Taylor's? What does this have to match? This has to match, if we did our math right, f of pi plus f prime of pi times x minus pi, and so forth, right? So if I collect together all the constant terms, I should just have f of pi out front, right? F of pi is what? It's pi squared. What's sine of pi? 0. And then e to the pi. So that's the n equals 0 term from the last series. There's your constant terms. How about the linear terms? Well, you got 2 pi. That's from this one, right? Minus 1 plus e to the pi, right? And you can see those. There's one here. N equals to 0 gives me the minus 1 right in here. And then, of course, n equals to 1 over here gives me this e to the pi over 1 factorial, also known as e to the pi.
Where did f of pi come from?
Remember, at the start of all this, we have Taylor's theorem, which says that if the function is analytic, it is, you can expand it by its Taylor series.
No, yeah, I know, but like from there.
Oh, from the line above, where did the pi come from, specifically? Just in terms of arithmetic of power series, this pi squared is that pi squared. And over here, this times 0 is that one. It's from the n equals 0 term in there. That series is 1 plus x minus pi plus 1/2 of x minus pi squared and so forth. Yeah. Okay, I got you. Good. Good question. Good question. And then, of course, we have the quadratic term, which I'll start us out with the 1 from this, right? There's a 1 from that. And there's also, is there any quadratic term in the sine expansion? Well, sine is an odd function. No. The sine of x minus pi has nothing to offer here at the x minus pi squared level. And we do pick up 1 from here, 1/2 e to the pi. X minus pi squared. Okay. Now, I will continue down here. Those are the oddballs, right? Next thing I'll do is just rewrite the sums we have above, okay? See, because in your problem 100, there would be more to do because you'd like to combine even terms together. You'd like to combine odd terms together for the best answer, right? But here, it so happens that we already just have even and odd, right? Is that right? No, that's still not true, is it? This one has both even and odd terms, right? This has just odd terms. So let me just pick on the even terms here. What does that look like? Let me use a k equals 0 to, well, I don't know equals what to infinity. I'm not sure about that. Something to infinity of e to the pi over 2k factorial x minus pi to the 2k. So I'm picking off the even part of that last series. Where do I start at? I'm putting n equals to 2k. I'm splitting off the even part of the series. I already used the quadratic in the formulation of the line above, right? So that starts at at 4. Like this, I want this to have the 4, the 6, 4, 6, 8, so forth. So that means I start k at 2. All right, so that starts at quadratic order, excuse me, at quartic order. And then how about the odd terms? I'll use a j. J equals something to infinity. And so what I'm going to try to do here is collect together all of the odd terms past linear order. So, you know, cubic and higher, where are those coming from? You have your minus 1 to the 2j excuse me, minus 1 to the j plus 1 divided by 2j plus 1 factorial. So that right there is just, I'm just changing n to j for the sake of, well, hopefully confusing you guys. No, that's not really my intention, but that's this piece, okay? I just changed the n to a j for the sake of, it just seemed like a good thing to do. Because over here, this I will actually sort of make a more, perhaps less trivial step. That's e to the pi over 2j plus 1 factorial. So the odd terms from the sine series and the odd part of the exponential series is right there. Where does that j start at? And what am I missing? Kind of important, right? X minus pi to the 2j plus 1 right there. My help for problem 101 is going to seem really, really simple after all this. Where does j start at? 1. Let's see, does that make sense? If we put j equals to 1, we get 2 times 1 plus 1, which is 3. That makes sense to me. We should start j at 1 because this series captures the cubic and higher odd terms. The linear one is already up here. And there you go. That is the power series expansion centered at pi for f of x equals to x squared plus sine of x plus e to the x. So there's 3 stages to this calculation, right? Like, number 1, decide your method, right? Number 2, execute the method, right? In this case, which was substitution paired with algebra, right? And step 3 is clean up the answer, right? There's partial credit to be had at each step of this. If you can only get past steps 1 and 2 and you can't do the last step, it's still worth something in here, right? But as a generic comment, like cleaning up the answer means collecting all of the terms which have the same type together in one piece. See, because if I do this, then I can answer questions that are related to this problem, like, what's the 50th derivative of the function? Can you guys tell me? At pi? So let me ask a slightly more leading question. What's the 50th derivative divided by 50 factorial equal to? I need to find x minus pi to the 50th in my expansion. See, I've collected all of the like terms together, so that's unambiguous. There's only one place that a 50th power can come from. It's what? Is it the j one or is it the k one? It's the k one, right? It's the even term. K equals to what? K equals to 25. K equals to 25 gives me x minus pi to the 50th, right? So this would be equal to e to the pi over 50 factorial. Therefore, the 50th derivative of this function evaluated at pi is e to the pi. Which you probably could have figured out without power series anyway, right? I think you could have, truthfully. I think a Calculus 1 student could figure this out if they believe they could. If you don't give up at the start of the question, you could actually answer that as a Calculus 1 student, because you just differentiate it. You start seeing a pattern. You think about what happens when you plug in pi. X squared is irrelevant, and the sign goes back to plus or minus sign at any even derivative. Actually, it goes back to sign at all even derivatives, doesn't it? So those are all 0. Yep.
I don't understand where you got prime of pi now.
This?
Yeah.
These are the first two terms in the Taylor series expansion, TF of x.
Oh, and then like in the power.
Oh, where did these terms come from? That's just from, I mean, we can look at it two different ways. On one hand, you could think about it in terms of just differentiating and plugging in pi. That's not what I did. Think about, how do I get, so I get this guy times what? Well, that guy alone gives me this 2 pi. Great. The minus 1 is, this is from n equals to, I think, 0. N equals to 0 in that one. That gives me x minus pi to the 1 power, which is x minus pi. And there's a minus out front. Minus 1 to the 0 is 1. 0 factorial is 1. So the first term in that is actually just minus x minus pi, which gives me the minus 1 from that. And then over here, when we get to n equals to 1, we've got an x minus pi to the 1 over 1 factorial times e to the pi, which gives me that e to the pi. And that's the source of those three terms, yeah. Yeah, so for your thinking, it's important to know 0 factorial is 1 and 1 factorial is 1. If you don't have these in mind, it makes it really hard to see where things come from in here. We must keep these in mind as we're calculating. Can someone give a hint on problem 101 now that we're got to that? Yep. It is indeed not a power series. Right. So if it's not a power series, how do you decide where it converges? I mean, what guides our logic? Yep. It is alternating. That's true. I also don't know if that's helpful. But you're right. Yeah. Any other ideas? Other ideas? Yep.
By the end turn test, in order to converge, it has to go to 0.
That's true. But if it goes to 0, that doesn't give us convergence either. I mean, definitely if that doesn't go to 0, we're in trouble. Sure. Yeah. But annoyingly, if it does go to 0, that's not enough. But we do have tests, right? I mean, you could use the ratio test. Right? But then you'd have to check endpoints. Can you? Oh, man. Huh. I think I meant to put like powers of n on that, x plus 10 and x minus 10. Yeah. Oh, the answer to this is very boring. Actually, I mean, Patrick is not far off. Because you can show it doesn't go to 0 for what? This is why I rejected yours, is I didn't think it was interesting when it didn't go to 0. It's actually very interesting where it doesn't go to 0. Where does it not go to 0? Is there any n dependence on the x plus, hey, plus or minus 10? Well, if unless x is equal to plus or minus 10, right? Then that means you're looking at some non-zero number. Suppose x is not equal to minus or plus or minus 10. You're looking at some non-zero number times this. Patrick points out that if n goes to infinity, that goes to not 0. Therefore, by the nth term test, divergent. On the other hand, what happens if you plug in x equals to 10? It's the 0 series. What happens if you plug in minus 10? It's a 0 series. So I'm sorry, I seem to have solved this problem for you. Find all x. It's 2 points, plus or minus 10. Those are the only points for which this series converges. But of course, you should explain this with what we just went through. To make this more interesting, put x plus 10 to the nth power, and put x minus n to the nth power. That's, I think, what I intended here. I've actually already talked about this another day. I talked about a bi-series, quote unquote, and this would be that. If I do this. So this is, of course, this is not required. I'm just telling you how to make the problem more interesting. Fortunately for you, I forgot to put the power n there. My bad. See, if you did this, though, which is what I intended, then could you recognize what it is? Which is a what? What's that? If I call this R, would that help? If I wrote 1 plus r squared, would that help? I mean, this is geometric, so it would converge for the absolute value of r less than 1, which is to say minus 10 times x minus 10 times x plus 10 less than 1, which is to say x minus 10 times x plus 10 less than 1. I personally like to solve this sort of inequality graphically. You've got 10 and minus 10 as zeros of a polynomial. Did I drop a 9? It's over here. So not quite the scale. What's the y-intercept here is like minus 100, right? So you're looking for x less than 1/9. Oh, that's kind of cute. It actually is not. So I think it'd be basically like all of this would be the x for which it converged in that related but different problem. Again, this was not assigned, sorry. But yeah. Again, it's not a power series, so it doesn't fit into our general theorem. Other questions? So yeah, problem 101 is kind of weird. That was the point. I wanted to draw your attention to the fact that if we don't have a power series, the domain can look quite different. I have time for one more question. Yep. What's that, 99? Okay. See, this is almost the same question again. So if you wanted to find a 100th derivative here, at what? At 0? So, I mean, if you go through what I'm just erasing right now for a given problem, this allows you to answer not just the question which is, like, not just the question which is posed in problem 99, but like all possible questions, right? And in terms of like derivatives of higher orders of the power of the function. But if your target is a specific number, then you can focus your attention on selecting parts of the power series expansion for the function which are relevant to the task at hand. All right? In other words, I'm looking for anything that produces x to the power 100 in the Maclaurin expansion for this function. All right? That's what my goal has to be, finding anything that can contribute to x to the power 100. Right? So we got to think about that. So I've got this f of x, right? I've got x squared, was x squared, plus x to the 4th, plus, what is it, x to the 6th? Sinh of 3x, plus cosine of x to the 4th, great. And then plus 1 over 1 minus x squared. Great. And I'm supposed to find the 100th derivative of 0, right? Yeah. So the concept here is to think about the expansion. This is equal to the sum n equals 0 to infinity of the nth derivative at 0 over n factorial times x to the power n, right? So if you envision that, that's equal to, well, f of 0 plus da, 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 da. Eventually, we get to 1 over 50 factorial, the 50th, 100 factorial. Still stuck on the last problem I made up. 100 evaluated at 0 times x to the 100 power. Right? That's there. It's somewhere. But this 100th power term is somehow built, it's constructed by the sum of the 100th power terms from the things that are making up the function, right? So when I think about this, I think about it, item by item. Like, can we find x to the 100th in, expansion for the following? Start with the first thing. If you got x squared plus x to the 4th plus x to the 6th times the sinh of 3x, will that have an x to the 100th power term in its power series expansion? Yes or no? I see a no. Why? Because this is an odd function, right? If you replace x with minus x, this just goes back to itself again. If you put in minus x here, you get minus sinh of 3x. Because this is odd and this is even. The product of an even and an odd function is an odd function. So no, there is no has no non-trivial coefficient for x to the 100 in the Maclaurin expansion. All right, so that's out. How about cosine x to the 4th? Does that produce something of order 100? Maybe. I mean, I'm not sure. So this looks like what? This looks like the sum n, well, let's say k, equals 0 to infinity minus 1 to the k over 2k factorial. And then I do a substitution here, x to the 4 to the 2k, right? I'm making a substitution into that Maclaurin series, which I need to memorize. I need to memorize this. This is something you should leave this course knowing. Cosine of power series, this is the power series for cosine. This we should know. Okay? Good students of Calculus 2 know this when they leave this course. So that's just 8 to the k here with the substitution, right? So I've got like a 1 minus 1/2 x to the power 8. And then what's up next? 8k. So it goes to what's next? 16, right? Like plus 1/24, 1 over 24 x to the 16th, and then so forth, minus 1 over, I don't know what it is, 6 factorial, the 24th power, right? Eventually, it gets to what? What's the pattern here? Let me state it a different way. This works out to x to the 8k, right? Can you get that equal to x to the 100 for some choice of k? It's like, well, you can. It's just that k is not an integer, right? You'd need k equals to what, like 12.5? This is not allowed, right? K has to be a whole number. It skips over it, right? We go from 96 to 104, is that right? I mean, it skips past 100. So again, the answer is nope. There does not exist an x to the 100th term in this one either. So what I'm doing right now is part of a larger thing that you should always think about doing in calculus, which is dividing and conquering, right? It's always wise to try to take your task and divide it into smaller tasks if you can. We can do that here. So what's left? One over 1 minus x squared, right? And how do I do that one? This is what we remember. What I start with, like the first about week we talked about this. I just did geometric after geometric after geometric, right? The reason I did that is because that is one of the first and most important examples. We haven't done it much lately because we've been focusing on the Maclaurin expansions, right? But it's still something we need to know. So this is the sum. Let's say j equals 0 to infinity of x squared to the j, right? So a equals to 1, r equals to x squared. It's a geometric series. So let me rewrite that. So what we're looking at is the sum, j equals 0 to infinity of x to the 2j. Does that produce an x to the 100 power term? If the answer was no, then the derivative is 0. But the answer here is actually yes, and we can put, so here's what I do. I say, okay, so I want 2j to equal to 100, right? So I'm going to look at j equals to 50. So after all of this discussion, what have I figured out? I figured out that this is equal to stuff, right? I really don't care. Plus dot 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 plus eventually, what's the coefficient of x to the 100? 1. So, since that's the case, I can compare this to the 1 that's right here. And that tells me that f to the 100, the 100th derivative evaluated 0 over 100 factorial is equal to 1. If I write anything more, I've solved your problems. I must stop. I must stop. Listen, the reason I assigned this problem, it wasn't so that you could suffer through it alone. It's so that we could have this conversation about techniques to solve such problems. All right? Does that make sense? I mean, I'm really just using all of the tools that I've been using for like the last 3 or 4 problems I've worked in here. It's really the same set of tools over and over and over again. Chief among them being that 2 power series are equal if and only if they match term by term by term, right? But in order to compare them, they have to have the same center, right? I can't compare a power series centered at 2 to a power series centered at 3 term by term. That won't work. You'll have to take one or the other of them and recenter them in order to make a comparison before you do. Recentering power series is unpleasant. All right, so anyway, there's that. I'm going to turn the page here and go to our next topic, which is differential equations. We still have, I think, half-hour class. That should be a good amount. So let's talk about differential equations. So, first of all, I suppose the first question is, what on earth is a differential equation, right? Can you guys tell me what is a differential equation? Let me write down a couple. dy dx equals to x squared y. Or we could have y prime prime plus y equals to 0, where y prime is equal to dy dt. Another example would be this partial squared v partial x squared plus partial squared v partial y squared equals to 0. These are 3 examples of differential equations. What makes a differential equation a differential equation? Yeah, what is that exactly? That's a partial. This is read partial. It's not a d, it's a new symbol. It may be something you've not written before. You probably need to develop your own handwriting for that. Which is kind of a... See, that's an experience that it happens to you pretty much only in math classes, right? You don't find yourself sitting in the middle of history class and all of a sudden they start, like writing the name of a Chinese emperor in terms of the original, like, pictographic symbol, right? Like, you don't find yourself needing to write new symbols in other classes, do you? That's just math, I think. Maybe there's an art class. But what I'm fishing for here is, it seems almost like I'm saying nothing, but I'm really saying something. A differential equation is an equation which meaningfully involves derivatives with respect to one or more independent variables. If the derivatives are taken with respect to just one variable, it's called an ordinary differential equation. So the first 2 examples here, these are, and let me put a y squared on this. These are ordinary differential equations. Or, as is often abbreviated, these are what are called ODEs. Ordinary differential equations. The differentiation is taken with respect to just one independent variable. For my first example, the independent variable is x. For my second example, the independent variable is t. my third example is an example of a partial differential equation. Partial differential equation. All right, a partial differential equation, or PDE, is a differential equation which involves more than one independent variable. All right? And oftentimes, the differential equation links these different derivatives in some meaningful way. This equation right here has a name. This is called Laplace's equation. You could think of V as being the voltage function. This is the equation that the voltage has to satisfy on a conducting plate. All right. In the presence of charge, you get Poisson's equation, which puts a minus rho over epsilon naught over here. If you add the minus rho over epsilon naught, then this is Poisson's equation, Poissons, which would be like if you're solving a voltage function where you have the presence of charge. Anyway, this is part of a larger story. Pretty much all of your basic equations of classical physics are partial differential equations, for the most part. Well, field equations anyway, like Maxwell's equations. Physics 232 basically is the story of Maxwell's equations. There's Gauss's law, Ampere's law, Faraday's law, and the no magnetic monopoles law. All of these collectively form Maxwell's equations. All right? These are all partial differential equations in the electric and magnetic field. The independent variables there are time and space. There are actually six dependent variables, the x, y, z components for the electric field, the x, y, z components for the magnetic field. So if you look at Maxwell's equations, there's a lot there. It's like a system of coupled partial differential equations. If you're a physics major, not here, and you'll spend multiple courses just learning how to solve Maxwell's equations. It takes literally 3, 4, maybe a half dozen courses to really gain competence in solving Maxwell's equations in real physical situations, right? So partial differential equations, it's often been said that a given partial differential equation is like its own world. To really understand a given partial differential equation, it could be a career for a mathematician to understand a single one really deeply. Ordinary differential equations is most of what Math 334 is about. There's a standard sequence of techniques that are known there. And in here, you start the story, right? I will teach you how to solve first order differential equations. This one right here is a first order. Why is it first order? Yeah. Yeah, because the highest derivative that appears non-trivially is the first derivative. What is the second example there? What's the order of that differential equation? It is a second order ordinary differential equation. The second is also what's known as the linear ODE. The reason that the second one is linear is because the dependent variable and its derivatives appear in a linear fashion. The first differential equation, this one here, is a nonlinear differential equation because of the y squared. If I change the y squared to just a y, if I wrote dy dx equals to xy, x squared y, then that would be a linear differential equation. Linear differential equations are very nice, and you'll learn in Math 334 how to solve a wide variety of them. So our focus in here is going to be on how to solve first order differential equations, but I think I've also asked you a homework problem which is kind of like, how would you solve a second order differential equation? You know one way you can solve a second order differential equation? It's pretty simple. You just assume that the answer is a power series and plug it in, and work out the dependence on the coefficients. Let me do that briefly here. Let's just do it to second order for my second example. How to use power series to solve ODEs. Number 1, assume solution is power series. Okay. Point 2, plug it in. 3, find conditions from 2. Listen, saying a function is a power series says so little about it from an applied perspective that it's just like a very, very plastic assumption. To say that something's a power series, that's it's like telling you, I met a student, and then you're like, well, can you describe them? And I'm like, they're human. You know, it's not really that helpful. So it's a very pliable idea. So step number 1 here just means this. You put y equals to, say, c0 plus c1x plus c2x squared, right? I'll just work to second order. So there's my assumption. It's a power series. Plug it in. I'm going to plug it into y prime prime plus y equals to 0, right? So what does it take to plug it in? I need to calculate y prime prime. What's y prime prime equal to? Differentiate term by term, right? What's y prime? It's c1 plus 2c2x plus da 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 da. So by the time you get to the second derivative, the leading term is 2c2. I guess the next one is what? Just for the sake of you seeing what I'm doing, that would be 6c3x, right? There we go. No, because the first derivative brings me down to 2c2x, and then I differentiate again for y prime prime, which just brings me down to 2c2. Y prime, in between step here, is c1 plus. It's okay. I'm just doing 2 things. I you know, my own stupid fault for trying to do 2 steps at once. There you go. Now everybody understands. 2c2 plus 6c3x. Plug it in. Y prime prime plus y equals to what? It's 2c2 plus 6c3x plus da 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 dot. And what was y? c0 plus c1x plus c2 x squared plus c3x cubed plus da 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 dot. What is this equal to? It's equal to 0 by assumption, right? So what does that tell you? If you look at the constant terms, we've got 2c2 plus c0 plus 6c3 plus c3, excuse me, 6c3 plus c1 times x, right? Plus, well, higher order stuff. I'll just look at the constant, I'm just going to look at the constant term and the linear term. That's enough. And so what this tells me is that c2 is equal to minus 1/2 c0, and this tells me that c3 is equal to minus 1/6 c1. So y is equal to c0 plus c1x plus c2x squared plus c3x cubed plus dot 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 dot. And you see that the even and the odd terms get grouped together. There's a linkage between successive even terms and successive odd terms in the solution. So like I can factor out a c0, and that will give me c0 times 1 minus 1/2 x squared plus stuff I haven't calculated, plus c1 times x minus 1/6 x cubed plus stuff I haven't calculated. There you go. Those are the first 4 non-trivial terms that appear in the general solution to the second order ODE. I hope you can see that using power series to solve it was actually not that bad. If you get down to it, like, this is a very kind of heavy-handed technique. Just assume the answer is a power series, plug it in, and then apply usual power series logic, which is that term by term, the coefficients have to match. The 0 series on the left-hand side means that all of the coefficients of various powers of x must be 0 on the right-hand side. Yep. Are these going to be on the test? Sure. Yeah, why not? There is a homework problem like it. That's why I'm talking about it at the moment. Yeah. What did I just do? You don't understand what's happening. So if this is equal to 0, then the constant terms, right, give me 2c2 plus c0 equals to 0. The coefficient of x gives me 6c3 plus c1 equals to 0, right? But if I solve that, I can solve that for c2, it gives me 1/2 c0. And I can solve the other one for c3, that gives me minus 1/6 c1. What do you expect the solution to a second order differential equation would look like? Is there a more simple example that you could look at to gain intuition? What would be the simplest second order differential equation we could possibly solve? We could have solved it in calculus 1. How about this? Yeah. Right. So C0 is C0. C2 is minus 1/2 C0. So that is minus 1/2 C0. So I can factor out C0, and it leaves me with minus 1/2. That's from that. Yes, the x squared was there to start with because we assumed that the solution's a series. The other one, this one here, the x is the x, c1x, and then we just found that c3 is minus 1/6 c1. So I factor out the c1 and leave the minus 1/6. This is not surprising, guys, because if you look at y prime prime plus y prime prime equal to 0, integrate once, what do you get? Y prime equal to c0, right? Let's say c1. Integrate again. So if you think about this, like generically speaking, a second order differential equation, independent of other conditions, should have 2 undetermined constants in the answer, the general answer, corresponding to the fact that if I give you how the acceleration works, physically speaking, I have to tell you a position and a velocity in order to fix the trajectory. Like, that's an intuition for what's going on here. But here's a mathematical example. Like, generically speaking, it should look something like this. So I'm not surprised that we needed a C0 and C1 in the answer, because there's not just one answer, there's a whole infinite family of answers. Finding a whole infinite family of answers, does that sound familiar to something you've done before this semester? There's not just one answer, there's a whole family of them. They're all differing by a constant c. What's that? That's integration, right? Solving a differential equation is just another kind of integration in some sense. I would be remiss if I didn't point out what we just found. What are these power series you're looking at? Can you recognize them? Sine and cosine, right. This is C0 cosine of x plus C1 sine of x. And if you, oh, I'm so sorry. My bad. Did I solve the differential equation which was stated